All right, so now we are going to discuss perfect graphs. So a graph is considered perfect if the clique number of every induced subgraph is equal to the chromatic number of that induced subgraph. So we're not only just saying that the chromatic number is equal to the clique number for the graph, which is the lower bound for the chromatic number, but that the same equality happens for every induced subgraph. So in applications, one reason we care about perfect graphs is that it turns out that certain calculations are quicker to do. So in general, finding the largest clique in a graph or the optimum coloring of a graph are what are called NP-complete problems, which means if you could derive a fast algorithm for solving the problem, then you will have derived a fast algorithm to solve any problem for which being able to check a solution runs quickly. And so some examples of perfect graphs we've already seen in this course are trees and forests and bipartite graphs. And also a complete multipartite graph also turns out to be perfect. So for trees, and forests, this follows because these are examples of bipartite graphs. And in all three cases, the chromatic number and the clique number is always 2 for any induced subgraph, unless the induced subgraph is an independent set, in which case both numbers end up being 1. Whereas here, any induced subgraph is also going to be a complete multipartite graph, and then the clique number ends up being the number of parts, and that also ends up being the chromatic number. So here I discussed 2 theorems about perfect graphs. We will not prove either of these in this course. The first one the proof can be found online or in various graduate texts for graph theory. So it has an accessible proof, but it's still quite hard. It says that a graph is perfect if and only if its complement is perfect. This was a conjecture a long time ago, which is why it has the name perfect graph theorem. However, there's an even stronger version of the theorem called the strong perfect graph theorem that says a graph is perfect if and only if the graph and its complement do not contain an induced odd cycle. I forgot to put of length greater than 5. You can see how the first theorem immediately follows from this one, because if G is perfect, then it and its complement do not contain induced odd cycles of length at least 5, but that also means the complement has the same feature, so the complement is also perfect. So this theorem, its proof, goes on for hundreds of pages across multiple journal articles. It's a really hard proof. So instead, we will focus on finding other examples of graphs that are perfect without using this theorem. So the first class of graphs we want to look at are called interval graphs. So these correspond to the following setup. So you have a collection of intervals, and here I'm talking about intervals in the calculus sense. So each of these has AI is less than BI, and these are real numbers. Then we are going to find the graph of the intervals to have vertex set corresponding to the set of possible intervals. So there are k intervals. Our vertex set are the integers 1 through k. And we're going to say I and j form an edge if and only if the ith interval and the jth interval intersect. And then a graph is called an interval graph if it comes from this construction. So we're going to eventually show that G is perfect. So let's look at what this means. Suppose these are my 4 intervals. Then I'm going to call these intervals A, B, C, and D. Then we see that A overlaps with B. B overlaps with C and D, and C and D overlap with each other. And so the point is, if we find a proper coloring of this interval graph, say color this 1, then we color this next one 2, then we color the next one down 1, and we see we have to color the last one 3, then this corresponds to coloring this intervals. And what this means is you've assigned a color to each interval with the property that intersecting intervals have different colors. In other words, you could suppose these intervals represented start time and end times for, say, class meetings, and then clearly you can't have two classes meet in the same room at the same time, so the coloring would correspond to a room assignment to ensure that all your classes actually run as scheduled. So the fact that this graph is perfect means that the number of rooms you need, the chromatic number, is equal to the clique number, the size of the largest clique, which means the largest number of intervals for which you have simultaneous intersection, it turns out. So in other words, if you have a moment in time, you count the number of classes that are meeting at that moment, that largest number ends up being the clique number. And obviously clearly gives you a bound, because clearly once you have, say, 3 classes meeting at the same time, you see you need to have at least 3 rooms. The theorem is that this tells you actually need exactly 3 rooms. Of course, instead of showing that interval graphs are perfect directly, we actually introduce another class of graphs called chordal graphs. And so there are chordal graphs that are not interval graphs, but the same thing ends up being true. In each of these 3 classes, a lot of known problems are quicker to solve. So what is a definition of chordal? Well, the definition of chordal in the textbook is the following, that if your graph has a cycle of length at least 3, then it must have a chord. So in other words, it cannot have an induced cycle of length 4 or larger. Or equivalently, every induced cycle is a triangle. So it's a bit hard to prove, but you can prove that this definition is equivalent to this other one, which is the one we're going to work with because it's easier to work with for the types of theorems we're proving. So we're going to say a graph is chordal if there's a vertex with the property that the induced subgraph on the neighborhood of the vertex is a clique. And when you remove the vertex, what's left is still chordal. So for instance, if we look at this graph I just drew here, if I take this vertex as V, I see its neighborhood is a clique, and I see that if I remove the vertex, I get a graph that's also chordal, because if I take another vertex here, its neighborhood forms a clique, and its deletion is just an edge, and I keep recursing. So this is an example of a chordal graph. It also turns out that forests are examples of interval graphs and bipartite graphs. However, in general, a bipartite graph isn't necessarily chordal, because obviously bipartite graphs can have even cycles of length greater than 4. So first, let's prove that every forest is actually an interval graph. All these proofs are going to be by induction on the size of the graph. So suppose you have a leaf of your forest, and let V be the only neighbor of that leaf. By induction, we know that if I remove the leaf, I get a new forest that is also the interval graph of some collection of intervals for some I. Let's focus on this parent vertex of my leaf. Let's take the corresponding interval, let's make it an open interval, and let's remove all the rest of the intervals from it. Now you can check using an induction argument or from calculus that when you do this, what you will end up with is a disjoint union of open intervals, Cj, Dj. And so what we're going to do is take the first one, C1, D1, and it's familiar that if you add the 2 numbers and divide by 2, you get the midpoint, but the midpoint's not an interval, so instead I'm going to take and divide the interval up into 3 equal parts, and then take the middle part. So it turns out these points have these coordinates, twice C1 plus D1 over 3, and C1 plus 2D1 over 3. So if I take this interval, I make this the interval corresponding to my leaf vertex. Notice that this interval is contained in C1, D1, which is contained in this union, which is contained in my original interval for AV, BV. So that guarantees that these 2 intervals intersect, and therefore, as an interval graph, I need to have an edge between L and V. On the other hand, since these intervals were found by removing all the intervals coming from our other vertices from V, we are guaranteed that this new interval we just built has to be separate from the rest. Because if there was a point in common, then that point would be in this interval, so it'd be in here, which means this intersection would be non-empty, which contradicts this construction. And thus I see that the interval graph given by this collection of intervals is actually F. So every forest is an interval graph. It also turns out that interval graphs are in fact chordal. So here the strategy is going to be that I take the interval that's the farthest most to the right, and I'm going to remove it from the graph, and then show that this interval, its neighborhood in the interval graph, is a clique. So by farthest to the right, I mean I'm going to let A be the maximum of my left endpoints of all my intervals. And then subject to fixing A, I'm going to let B be the maximum of the right possible endpoints. So I'm going to remove this interval from my collection of intervals. And I know this interval is of the form AJ, BJ for some J. So then the interval graph given by the rest of the intervals is just G take away the vertex J. By the induction hypothesis, we can assume G take away J is a chordal graph because it's an interval graph. And so now, in order to complete the proof, I just need to show that the neighborhood of J is a clique. And that's going to take a little bit of effort. So let's take an edge from I to J. Then I'm going to claim that A sub J is actually in the interval AI, BI. So in other words, in order to show that I have a clique, I'm actually going to show that all the intervals that intersect my chosen one all have the left endpoint in common. So by definition of AJ, AI has to be less than or equal to AJ. And because of the fact we have an edge between I and J, the ith interval and the jth interval have to intersect. So there has to be a point in the intersection. Since this point is in the interval AJ, BJ, X has to be greater than AJ. Since it's in AI, BI, it has to be less than or equal to BI. And as already noted, AI is less than or equal to AJ. So now I see AJ is trapped between AI and BI, and so I can conclude AJ is in the ith interval. So what I've seen is that if I have two edges to J, then little aj is actually in the ith interval and the kth interval. And so in particular, the ith interval and the kth interval have to intersect as well, and so I get an edge between I and k. In other words, for any two neighbors of J, there's an edge between them. So the induced subgraph on the neighborhood of J has to be a clique. And thus, G is in fact a chordal graph. Finally, we need to show that chordal graphs are perfect. So let G be chordal, and let V be a vertex with the property that the induced subgraph on the neighborhood is a clique, and deleting the vertex gives me a chordal graph. By induction hypothesis, I can assume G take away V is in fact perfect. So now I need to show that G is perfect, which means I need to show that the clique number of any induced subgraph on G is equal to its chromatic number. And so let's take a subset of vertices. If V is not in S, then the induced subgraph on S is actually a subgraph of G minus V. And since G minus V is already perfect, we already have this equality in that case. So then let's consider what happens when V is in S. Well, then, since the induced subgraph on S take away V is a subgraph of G minus V, I already know by induction that the clique number of this subgraph is equal to its chromatic number. So let's let F be a coloring with the right number of colors of the induced subgraph on S take away V. All we need to do is show that we can extend the coloring to the vertex V, and then we have a coloring of the induced subgraph on S. So let's do that. Let's take two neighbors of V that are both in S. Since we already know that the induced subgraph on the neighborhood of V is a clique, it follows that these two have to be adjacent, which means that f of u can't be equal to f of w. In particular, if I let A be the set of colors of neighbors of V that are in S, then I see that each color gets used exactly once in this set. There's no repeats, and so the size of this set is equal to the number of neighbors of V that are in S. Since this forms a clique, I know that this is bounded from above by the clique number of the induced subgraph on S take away V. We're going to call that B for right now. So if I have strict inequality here and A is less than B, then that means that not every color got used for the neighbors of V, and so there must be a color left. So it's possible to extend F to color V. So that's great. What happens if A is equal to B? Well, in that case, the intersection of the neighborhood of V with S has to be a maximum clique because it's the same size. And in particular, if I add V to this set, I get a larger clique. So it follows that the clique number of the induced subgraph of S of G is strictly larger than this other one, which means in this worst case scenario, every color got used. It turns out we actually are guaranteed to have one new color we can add and use to color V. And thus we see we can color the induced subgraph of G on S with omega colors. And therefore, if G is chordal, then it must be perfect.